Hey everyone, so this video we're going to use MATLAB's own built-in differential equation solver called ode45 to help us solve a differential equation. I want to give a little bit of background, sort of the 1,000-foot view of what this algorithm does, and then we can implement it for an example pertaining to a predator-prey system. So the first thing I want to say is ode45 is what we call a fourth-order Runge-Kutta differential equation solver. And it's a fourth order Runge-Kutta method, but it also has what we call a variable time step or an adaptive time step. So in the business, Runge-Kutta methods are a class of numerical differential equation solvers. And in comparison to what we've already talked about is Euler's method. So we're going to directly kind of compare some of the benefits that we get or we gain from using this so-called fourth order Runge-Kutta method in comparison to what we know from Euler's method already. So the long and the short of it, some of the benefits we have is number one, it is just more accurate. So for comparing kind of accuracies, Euler's method is only first order accurate. However, our Runge-Kutta fourth order scheme, or RK4 if you will, as maybe mentioned above, this is fourth order accurate. And you can derive these types of error estimates from a numerical analysis course or something like that. For us, what's very nice about this ode45 method is we can actually set the accuracy. And basically we can set the accuracy threshold, or in other words, this error threshold that we set will help us determine what the solutions are. So if we want a very accurate solution, we could specify that right up front. If we want a lesser accurate solution, we could also specify that. Which brings us into the second point. In comparison to Euler's method, this RK4 or Runge-Kutta method is a lot faster as well. So if we wanted to say get a certain accuracy with Euler's method, and we want to get a certain accuracy with Runge-Kutta, our fourth order here, we could do that. It's just that the Euler's method would take a lot longer. So in a nutshell, it would take the computer a lot longer to solve with an Euler's method to obtain the same accuracy as our Runge-Kutta 4 method. And the reason for this is this ode45 uses what's called an adaptive time step. So once we go ahead and set the accuracy that we want for our solution, ode45 will use the largest time step that we can do or that we can use to satisfy that type of accuracy. However, it's adaptive, so what time step we take in one motion forward in time doesn't have to be equal to the one we've previously used or the next one we'll use. So we can bounce around between how big a jumps in time we want to take to basically satisfy some error thresholds. And that's all I really want to say about RK4, this Runge-Kutta fourth order scheme with adaptive time step. ode45 is more accurate. It takes the computer also less time to actually get a solution with the desired accuracy. So with that, let's actually jump into the problem that we want to solve. And like I mentioned very briefly earlier, we're going to do a predator-prey problem with the so-called Holding type 1 functional response term. That is that interaction term on the right-hand side of our two differential equations here. But in a nutshell, this is a standard kind of predator-prey model. It's two coupled differential equations together, and we're going to see how to do that using ode45. I also want to emphasize here that we could have used ode45 for 1 equations, 2 coupled equations, 13 coupled equations, 100 coupled equations. It's a very, very versatile differential equation solver. And it's the number of equations that we use, we'll see how we can kind of change that as we go along in the code. But for right now, what's important to pick out, we have some differential equations we're going to solve. We also have their initial values. So we have 2 populations here, an X and a Y, corresponding to predator and prey. Actually flip, X is the prey, Y is the predator, but we have 2 initial conditions, one for the prey, one for the predator. And then we also have all of our parameter values that we'll set ahead of time. And then of course, the last thing is we want to know just how long do we actually want our simulations to solve for. So we're going to say from time 0 here to time 200. Otherwise, that's kind of the introduction to the equations we're going to use. 2 coupled differential equations. Let's go ahead and solve this thing using ode45. So in MATLAB, I'm going to click on New Script, and let's start writing this thing together. So I will call this function, say predator prey 45, or ode45. I'm just going to go ahead and save that. So let's start talking about what this script needs to have. It's going to look a lot different than when we actually wrote our Euler's method numerical solver. And a lot of the reason for that is, well, we're using a MATLAB built-in numerical solver now, so we don't actually have to do the time stepping ourselves. That'll be taken care of. But we have to basically pass it all the necessary information about what is the time, when does it start, when does it end, what are the parameter values, what are the actual equations we want, what are the initial values. All of that information we need to basically go ahead, pass it to this differential equation solver so it can do its thing. So let's go ahead and start doing that. The first thing we'll put in is the time information. And of course, like you've seen me do in the past, I comment a lot in the code. So I'm going to have something I call t-start, which is just our initial time of the simulation. And then we have our basically t-final, which we said was equal to 200 down below. So if you remember, we're basically at this stage of putting in our time information down below. So we're just specifying a couple variables now. The next thing, let's go ahead and shift gears and start inserting our initial values. So our initial values we'll have for each population, we'll have the initial population for X is 25. This is the prey. And we'll have the initial value of the predator be equal to 5. Now, the thing that's going to be a little different than what we've done before for initial values, we're actually going to go ahead and store these in a vector, which I'm just going to call initial values. And we're going to see that the reason I'm putting this into a vector is because we're basically just going to take this in these initial values and pass them into the MATLAB function in a few moments. In fact, we're almost at that stage to go ahead and do that. So let's start setting the stage, if you will, for actually solving this thing using ode45. And the first thing that we're going to do is actually start specifying the error thresholds or the accuracy that we want for our solutions. And the way in which we can do this is we can set what are called options that we'll use to basically pass these options into our differential equation solvers. Again, basically passing it a ticket that says, hey, I want this to be this accurate. And the way we can do this is using this using this quantity that's called ODE set. And as you see, when I open the parentheses, MATLAB brings up a bunch of options that we have here. And you can, of course, Google this to investigate this more. The one that we want is a relative tolerance. And this relative tolerance is basically setting that type of relative accuracy as we keep marching forward from one time step to the next time step to the next time steps, or each successful jump forward in time. And we'll set that accuracy at 10 to the minus 4, 1e minus 4. All right, so that's the only option we're going to use here, but there's other options that you can also employ in this algorithm. And what we need to do next is actually go ahead and start handing it all the information it needs. So when we actually use ode45, it's itself a function called ode45. We want to pass it in some right-hand side of our differential equation. So we'll say, hey, at this function f, that we'll need to specify in a few moments. And then we can start passing in all the other information. So for example, we can set a vector of t start to t final. So we're passing in, hey, when do we want the simulation to start? When do we want the final? What do we want the final time to be? We can then go ahead and pass it in our initial values in the vector form. And then we can also pass in our options ticket that we had before. So again, this options is just where we're setting all of those relative error tolerances, or those relative error accuracy specifications. But that's pretty much it. At this point, what this actually does for us is solve our differential equations. Now we haven't actually specified those differential equations yet. So let's go ahead and do that next. But I want to say at this junction, it's going to pass us back two things. It's going to pass us back the times and the solution values themselves, except it's going to give us those solutions in a matrix form. So let's go ahead and set those right-hand sides of our differential equations. And to do this, we get to define that function f that we're trying to pass into ode45 itself. So let's go ahead and do that next. So I'll just say this is another function. So this is another function contained within the same script. And we'll say that this is the right-hand side function for ode45. And inside this function, we actually specify our differential equations. So let's go ahead and write this function next. So we'll need to say function because we're creating another function. And then we can create something that we just call dvdt, which we'll see in a moment is going to be a vector of all of our right-hand sides of our differential equations. But this is equal to f, again, because that's what we're calling what we're passing into that ode45 on line 21. And this is going to be a function of t and our solutions that it's computing for us. Now, we're going to have to break this apart a little bit, so please try to follow carefully. That solution quantity, SOL, is basically the solutions containing both X and Y information. So at this junction, we're going to get to store our solutions from that vector first. And that sounds a lot fancier, but really what we're going to do is just say, you know what? Let X equal what's in the first quantity. And that's going to be our prey values over time, or at one specific point in time. Similarly, in the second component will be our predator value. And it's going to be our values from our previous time steps, actually. And similarly, we'll do the same thing for the predator. And the reason why we want to do that is, well, now we have what values were previously at in terms of X and Y. So we can use those to jump forward in time next, or this algorithm can do this in other words. But before we do that, we need to specify our parameter values, which we have not done yet. So if you're keeping track of what information we used so far, we've used the initial values. We've used the time information. Now we get to use these parameter values. So let's set all these parameters down here. So here we have K is 0.5, which is our logistic growth. And this was for the prey. We have our carrying capacity, which we set to 120. We had our natural death rate of the predator, which was 0.1. And we also had this interaction rate, or successful predation rate, called Q. But this was our interaction rate, essentially. Let's just go ahead and call that our interaction rate. But anyways, we are specifying a number of parameters. We could specify a whole lot of other parameters if we wanted here. This model just has those 4 though. So therefore, we've used those parameter values. So we're finally at the stage where we need to specify the actual differential equations we're solving. And we do that by basically telling this function, what is the right-hand side of those differential equations? So we'll say right-hand side of differential equations here. And to do this, I like doing this in a format that feels very similar to what the equations say themselves. So I'm just going to store what that right-hand side is in terms of the previous value of our solutions, X and Y, from lines here, 36 and 37. So dx dt is just going to be one individual number. So in this case, we take X and Y, and we just recreate those right-hand sides. And now notice, this is a lot different than what we did for Euler's method, where we're talking about specific components of our solution vector. Here, in ode45, we're already grabbing a specific solution component in lines 36 and 37. That's why we can just use X and Y's here. So that was our prey differential equation. And for the predator, we can do something similar. This is minus d times y plus q times x times y. And again, what we really care about in this case is the right-hand side. The fact that we're calling this dx dt and dy dt is really just helping us notice which differential equation are we talking about in terms of the right-hand sides. But once we have those right-hand sides, we actually need to store that information into a vector itself. And this is, if you notice, if we go back to the top of our function here, we had dvdt is something that this function is passing back once it gets in a t-value and a solution value. So we need to hand it back this vector that we're calling dvdt, which you can think of as it's a vector of all those right-hand side values. So in this case, we're going to put those into this vector, dx dt and dy dt. Now, the only thing that I want to emphasize here is what ode45 needs is we need this to be a column vector rather than a row vector. So the way in which we've put things into this vector right now would create a row vector. So we can just use this apostrophe that says, hey, take that row vector and transpose it to a column vector. right, and that's pretty much it. We created this function f that again is what is getting used by our ode45 function from line 21. And this function f, we pass it back the right-hand side information of our differential equations that's all contained in dvdt. And in this function, we listed all of our parameters, and we finally used our differential equations from our predator-prey model. Now, the only thing left is, well, hopefully that we're solving this in line 21, but let's actually do something with the solutions. So let's go towards plotting the solutions. And the first thing we're going to do is just store the solutions into their own vectors, because what is getting passed back by ode45 is a vector of solutions. So in other words, what sol is a matrix containing all solution values, both x and y, at each time step computed. So what we get to do is basically pull apart this matrix and store the solutions appropriately. And I will just say for us, the first thing is the number of rows equals number of times steps saved. And the number of columns equals the number of equations solved. So what this tells us is each column corresponds to a different solution vector. So either X or Y in this case. So let's go ahead and see how we can do that using MATLAB. So we can say, you know what? I want to grab all my solutions for X. So I can come into this matrix and say, I want to grab every single row out of the first column, which will give us that first column in the matrix. Similarly, we can come across and grab that second column of the matrix, and that corresponds to the prey, or the predator, excuse me. And now you'll notice, well, time, that's all the time points in which we actually computed the solution at. So next we can actually start plotting this stuff. So I'll make our fancy plotting attributes as usual. So we'll say line width is 5, say marker size is 25, and say font size is 22. And these are just our plotting attributes. And then we can come across here to actually start plotting. So if we want to start plotting something, we can say, well, put this information on figure 1. We can plot. Well, we're passing back that independent variable t. And then we can start plotting that against all the solution vectors for the prey. And we can start specifying what attributes do we want to basically make this plot a little prettier for us. So we can say, you know what, let's make it blue. So there's that B. Let's do a dash. Let's put a period in there so we see each time point as well, besides the line. And we can specify our line width, our marker size, etc. And we can tell it to hold on. So it'll keep plotting everything on top of it. So another thing, let's plot our predator population. So I'll just copy that line. Let's make the predator population red to distinguish it. Otherwise, again, we're plotting the independent variable t against our solution values at those time points, in this case, the predator. And let's label some stuff. So X label, this is time. Y label, these are our populations. And then we can specify a legend, let leg equal legend. And now the first thing we plotted corresponds to the prey, so we'll put that first into the legend. The second thing was the predator. And then finally, we can start setting other things like the font sizes and stuff like that. So setting the font size for the axes, we set, and then GCA, and then font size and FS, where we specified our font size up in line 36 here. And then we can set the font size for the legend as well. And hopefully that does it. I mean, we'll see. We just coded up, I don't know, 100 some odd lines. Let's see if this thing actually works. We'll go to save. Let's go to our MATLAB command window, and let's try to solve this. And lo and behold, there is our predator-prey solution for these particular parameter values. I hope this video was useful. And again, as we went through ode45, you could see possibly the areas in which, hey, what would happen if we just had one equation? In fact, let's visit that idea together. If we just had one equation, well, we only need one initial condition. Otherwise, everything here remains the same for actually using ode45. We'd only have one solution. We'd only be plotting one solution versus time, okay? And then how's the right-hand side of our differential equations going to change? Well, we only need to specify one dependent variable instead of two. And then we only need to specify one right-hand side function for a differential equation. And then we can just go ahead and store that one right-hand side into this vector. So instead of having two quantities, this vector would just have one. And in a similar vein, we could ask ourselves, what would happen if we wanted to couple three differential equations together? How would that change the code? And you could do a very similar exercise. Instead of two initial values, we would need three initial values. The ode45 function here would remain the same as long as we put in that third initial value into our initial value vector. We would get another solution from our differential equation model that we could plot the solution of. Otherwise, we just need to add more things into that right-hand side function of our differential equations down below in this function f. So I hope this video was useful, and have fun computing.